Hello everyone. So I hope you all have returned from the break. It's 1 p.m. Eastern Time, and with this, we are going to start our remaining schedule. We have finished three presentations, and now with this, we are going to start our next presentation. The topic is Introduction to 3D Printed Polymer Concrete by Design, and I am very happy to introduce our speaker for this presentation is Dr. Mahmoud Taha. He is the Dana Wood Research Chair and Distinguished Professor at the University of New Mexico, where he has worked for the past 21 years. He has authored over 400 papers, holds 15 US patents, and has advised more than 50 MS and PhD students. Dr. Reda Taha is a fellow of both the American Concrete Institute and the American Society of Civil Engineers. He is also a licensed professional engineer in the US and Canada and leads a startup focused on nano-modified polymers. So we are very happy to have you, Dr. Reda Taha, and let's welcome him and listen to his presentation.
Thank you very much for the nice introduction, and thank you everyone for being here. I really appreciate the opportunity to speak in this next virtual seminar about our work on 3D printed polymer concrete. The work I'm presenting is work done by my research group at the University of New Mexico. So I'm going to talk a little bit about polymer concrete. As Aparna said, this is a material I've been working with it for the past, I would say, 30 years or so. We'll talk about our new research and work on 3D printed polymer concrete by design, the thought about it, and the mixed design for the polymer concrete. The way we do the preliminary assessment and the rheological characterization, and then simulation for the printing, and then the performance characterization once we start doing the printing. Then we'll give a case study of a new work we are doing on what we call as acoustic black hole structures using 3D printed polymer concrete. Then we'll wrap up with some conclusions. So the polymer concrete, interesting material, little different than the typical materials we've been using. There are multiple types of polymer concrete. As you can see here, there is what we call as latex modified concrete. There is polymer impregnated concrete, and there is polymer concrete. The latex modified concrete is a case where we add a polymer latex to the normal concrete as we know it with the cement and the aggregate. Polymer impregnated concrete is a type of concrete developed in the early 50s, 1950s and 60s. And basically you produce a porous concrete, then you impregnate it with polymer, and then you polymerize this polymer inside. And then the third is the polymer concrete, where we completely replace the cement binder with a polymer binder. And we have the polymer concrete. The first type, the latex modified concrete, is considerably used in the industry today. Polymer impregnated concrete completely not used in the industry today. It's been not used for the past 20 years or so. Have some early interest in it, and then that interest died. Then polymer concrete, which we call a PC, which is the most used polymer concrete in the industry, and that's where my work here is focused on, and the presentation on 3D printed polymer concrete is focused on. In that case, the material is basically, we have, as you can see here, aggregate, and we have a polymer phase. There is, of course, voids, and then the polymer phase, and then there are fillers. The aggregate basically is typical aggregate we use in addition to fillers. The interfacial transition zone in this case is completely made of the polymer binder that connects with the aggregate. Example, many polymers are used, thermosets, including epoxy, vinyl ester, polyester, methyl methacrylate, and recently more work we've been interested in doing is with PEEK and Ultim as high temperature thermoplastic polymers. This is our thought about the 3D printed polymer concrete by design. We start from the far left here, where we do the mixed design. So mixed design including the polymer, the aggregate. We do some early qualification of the classical qualification we do for concrete, knowing how much strength this material will do. But before we do this, then we do some preliminary assessment, and I'm going to talk about every one of these in detail. The preliminary assessment give us a sense of that would this mix be printable or it wouldn't be. And if it is printable mix, then we move to the next stage, which is the rheological characterization and early edge strength analysis, because that is important to be able to model the 3D printing process as we are showing it in design simulation. That helps us to actually that design to combine material properties and also look at the specific structure we are designing, like the one we are showing down there, printing. What is the speed of interest? What is the geometry of interest? How long it would take us? What is the setting time? All these parameters. Now we can simulate it, and then we move to the next step. Once we do this, where we can actually do some performance characterization of that specific polymer concrete to make sure we are getting what we designed and we are getting what we achieving the material of interest to us that we can print with, and then we go for printing. So the material, basically, as I said, it's polymers and aggregate, and you can use the rule of mixtures for, of course, getting the properties. But the design is typical design of concrete, where we can combine both the normal aggregate, whatever it is, limestone, sandstone, any other type of aggregate of interest, along with some fillers. Fillers usually help us to get the consistency of the polymer. Multiple fillers exist, and we used many of them in the past. And with this, you can use different types of polymers as well. The most common, as I said, are the thermoset polymers, typically used with different aggregate. I'm showing here different types of aggregates used in polymer concrete. In our case, we do a nano-modified polymer. So we modify the polymer itself first before we mix it with the aggregate. The objective of the nano-modification is to add some specific properties or characteristics to the polymer concrete. Example mixes we're showing here from work we published before, including a mix where we did it with vinyl ester with a compressive strength of 60 megapascal. That is close to 9,000 psi in 7 days, and setting time of about 2 hours. This is another mix we did with methyl methacrylate with a strength of about 58 megapascal, very close again, about 9,000 or 8,000 psi. And in 7 days. So high strength materials and the the technology for using polymer concrete is well established, studied before. We've done a lot of research on it over the past 20 years, but here we are more interested in taking it to the 3D printing. So the preliminary assessment we do is to look at, basically, of course, to do visual assessment, but two things we look at. We look at both the slump and the slump flow. There is research published from Taha from 2019 and other research, including our work on polymer concrete, showing typically the material will be printable if we have a slump within the 4 to 8 millimeter and the slump flow in the 140 to 190 millimeter dimension for slump flow. So we do this test. Now, this is not cast in stone. It depends on a lot of variables we are having and the different materials we are including in the nano-modification of the polymer. However, at the end of the day, usually if you are in that window, you should be able to get a good printable concrete. So that's the first thing we do once we come to a mixed design for our polymer concrete. The next step is to do rheological testing of the material. The idea is to determine exactly what is the rheological behavior, understanding the flow. Of course, this is, we're explaining here the different factors affecting that flowability or rheology of polymer concrete. For example, the different effect on the matrix itself, because when we do nano-modification, that could affect the cross-linking of the material, can affect the viscosity and the viscosity evolution. We also look at how does the shear stress of the material change with time. Usually polymer concrete have been following a Bingham model and Bingham pseudo-plastic model. That's for most of the work we have been doing. But determining this is very critical for us to know how flowable is the material and if we need to do any changes in the mix design to actually allow the material to be flowable. Once we do this, then the next step is to actually start using this to model the polymer concrete. We need to model the printing process. To model the printing process, we have to identify the failure criteria for this, what we call as green concrete or the green material, the fresh material as it's placed, because in the case of 3D printing, you're going to be placing the material and building on it. So we need to know how does the more column failure criteria actually change with time. In that case, for example, we're showing here what was changing with time is both the cohesion and the friction angle. So to do this, this is an example. We are printing the material here, but we do that shear test where we apply a normal force and we apply to varying normal force. Then we apply a shear force to the fresh material to determine actually both the cohesion and the adhesion. Classical test done in geotechnical engineering, we use it to evaluate the material evolution with time in the case of polymer concrete. This is the case for a polymer concrete we did. And we start testing with time. We start from 0 minute to 30 minute to 60 up to 110 minutes, about 2 hours. We apply a load, in this case, a very low load. This was a 60 MPa polymer concrete, apply 1.1 Newton. And as you can see that the shear stress at a very low time, almost zero. It's not zero, there is some friction. And you can see the shear stress is increasing with time. And then there is clear jump in the shear stress close to 60 minutes or about 60 minutes in this mix we have been doing. And then it's considerably grow as the materials start to solidify, because at that time window, the material is still not hard. It is still soft, printable material. But between 60 and 90, as you can see, there is a good change in it. This is, I'm showing here the fact that at time zero, the value is not, we can see it here like zero, but it is not really zero. If you look at the resolution, there is growing shear strength of the material with time. And this is immediately after printing. We start from immediately after printing to actually, or yeah, to about 2 hours. We repeat the test at a different load. As you know, for this shear test, to get the envelope, you need to change the axial load and you measure again the shear strength. And as you can see, of course, as you increase the load, the value for shear is increasing because of the friction of the material. But we also can see a dramatic increase after 60 minutes. So we use this to actually find the cohesion and the adhesion. And as you can see, we are plotting the normal stress versus the shear stress at different times. And we basically bringing this envelope. You can see that envelope, the green line here, is representing the change in cohesion in the material. And you can see that significant increase in cohesion after 60 minutes. And then they also, of course, was the slope for the adhesion. So we can calculate or actually find what is the cohesion and what is the friction angle with time. So this is the model we came to. We now have a time-dependent model that describe both the cohesion and the friction angle with time. This is important so that you can actually use this for modeling as a time-dependent process for printing and for the strength development of the material. So to answer the question, why 60 minutes? In this case, we are doing, so we need to do some thermal measurements, because in the case of polymers, you have polymerization happening. So we use what is known as the ATT method. And basically, we measure the temperature. The black line here is showing the temperature evolution with time. dT by dt is the derivatives. And it's well known in the literature that when you have the peak of the derivative, that's basically the polymerization is happening here at 60 minutes. That's the gelling time. So very clear from the measurement matches exactly what we saw in the growth of the cohesion and adhesion, that at 60 minutes for our mixture, we have the gelation. Now, the good thing about this knowledge is you can actually use it with the polymers to actually, you could delay it a little bit or you can extend it a little bit, a function of the printing. That's why we call it polymer concrete by design, because we need to know it's not going to be one mix fits all. It's a function of the dimension of the design that you want to do for 3D printing and the speed you want to do this design with. And then you can go back and revise this material mix design to actually reach the time of interest. We also do here the evaluating the different mechanical properties at the time. So we do the compressive strength of the material to evaluate. The objective is not the compressive strength. The objective is to evaluate the Young's modulus of elasticity of that green concrete at different times. So basically, we cast the concrete. We have that special shape rod to actually measure the displacement of the material under load. We're coming recently with more new techniques to do that process and to calculate the elastic modulus, because that test, as you can see, is extremely complex and difficult to do, given that the material is flowable and is fresh, especially at early time. But using this, we can actually find the evolution of the compressive strength with time in minutes. You can see it here. And we also can evaluate the evolution of the Young's modulus, the elastic modulus with time. So we have equations here describing the elastic modulus increase with time, and we have equations, as I said, showed before, describing the failure envelope. These are because both the elastic modulus and the failure envelope are very critical to actually do the modeling. So that's an example of a model we were printing. This is printing a circular a model with 3D printed polymer concrete. This is the same material. We actually did its evaluation. And the idea now, we can do the modeling of the material and start observing what are the deformation happening, that is the stresses happening. Now, the finite element model used here is acquiring or incorporating both the failure mode and the elastic modulus growth of the material, because the material, when we reach this layer, on the bottom, for example, has been 60 minutes. So you actually have the Young's modulus at the bottom different than the Young's modulus at the top, as well as the cohesion and friction angle. So you can use this to estimate what is the stress contours, what are the displacement contours. You also can use this to see, does it make sense to develop these stresses at the time for printing. We're showing here the evaluation, the simulation, and the 3D printed polymer concrete that we did for, this is the 60 MPa polymer concrete. We use this to actually also try to figure out failure. So in the finite element model, you see we are expecting, once we reach this number of layers, we are going to start having failure here, which actually we started seeing here at about 10th layer. We can now go back in the model and start seeing that again, the evolution of the stresses and the deformations that is happening at different layers as we are printing. Once we do this, now we know what are we printing, we know what is the mix design. The last thing is to do some performance characterization of the mix. This is, for example, a different mix here we're showing, but we need to test before we go for the printing both the extrudability and the dimension stability of this mix. So this is a function of the how the speed of the rotation for the extrusion is represented in radian per second, as well as the velocity of the nozzle. So we repeat this process of measuring the changing the extrusion speed, changing the velocity of the nozzle to get the different shapes of the material we are getting and see what is the quality of the printing and the effect of those parameters on it. And to do this, we use two factors, basically the A sub P, which is the ratio of the printed area to the ideal area. The ideal area is the ideal area we would like to have. Also the speed, the 3D printing speed we have with a ratio to the extrusion speed. And then we look at this chart, and we typically have been seeing that for 3D printed polymer concrete, the value of the V star here in the 200 to 300 with a ratio of the printed to ideal value within a 1, something in this window will give us a good quality polymer concrete to print. The next step is to do the buildability, because now we are going to print. Of course, you should have a reasonable idea now on the buildability from the finite element model we have, but you can, of course, use the classical equation for predicting the buildability of the material, just to know what is the height of the material at which you are going to start seeing a material failure. And then you can do the printing. This is examples here of the 3D printed polymer concrete, where we actually are doing it as a textile reinforced polymer concrete, where the polymer concrete is printed and then we're putting textile reinforcement in the middle. This is for a special application of textile polymer concrete slabs. This is another example again of printing. I don't think this video will work, but anyway, that is the overall concept of 3D printed polymer concrete by design. And once we do the printing, as we're showing here, we can go back and fix some of the values either in every one of the steps we determined, and repeat this process to get a very good idea about the structure we are printing. I'm going to end up with a case study. This is a new work we've been doing. We worked it in the idea of developing what is known as acoustic black holes. Acoustic black holes basically are materials. The interest is to basically decay noise, decay signals, acoustic signals. That could be elastic waves or could be acoustic signals. How to do that through a structure where it is subjected to these waves, and you would like these waves to basically die. Very well known, there is a classical theory in acoustic black wave showing how to do that theoretically. And the idea of the acoustic black wave, I'm going to present this. I hope you are seeing that video. So it's showing the uniform beam and the acoustic black hole beam when you actually get this frequency to completely die. The difference, the idea is if you, in the theory, if you actually can change the structural geometry of the beam using that curve that's following this equation, you actually will get the signal, elastic signal to completely dissipate. Now, the idea we have is, can we, rather than doing this, doing it with 3D printed polymer concrete? There's a lot of applications for acoustic black holes, and we are actually involved in this through work with Sandia National Laboratories for developing it. Many applications, materials that can be embedded in structures that would actually result in decaying elastic waves. Our idea is that there is a limitation in acoustic black hole structure of the materials as used, and people observed that who did research on this, that actually with the decay in the signal in the structural thickness, you actually result in failure. So fatigue is a big problem, and a structural failure because of the reduction in thickness is a big problem. So alternatively, our idea was to actually change the material elastic modulus along the length, and that will result in a similar behavior rather than changing the thickness. And as we are printing, we actually can do that using 3D printing. So our goal in this case study was to explore the use of polymer concrete in making 3D printed polymer concrete, actually with making a multi-material. With multi-material, he is basically multi-type polymer concrete in making the acoustic black hole structures. And we think that we can actually change this polymer concrete during printing to keep appreciable load-bearing capabilities and to actually achieve the attenuation of the vibrational waves. A lot of advantages if we can do this because of the lightweight of the material. The polymer concrete by virtue have excellent damping characteristics, very good bond strength, which allow you to use multiple materials without a worry on bond. The ability also to fine tune the material properties and the high flexibility of the material. So it's very good candidate for this. And the idea is that, as you can see here, if we can print multiple layers of polymer concretes with varying properties, now the acoustic wave, if it's starting from here, basically the acoustic waves will die completely. Rather than, so in this sense, our polymer concrete stiffness changing, but the thickness doesn't change. And we can do this both in the horizontal or vertical shape with 3D printing. We looked at the different variables affecting this, including the constituent material of the material, the polymer properties, the filler properties, and also the nanomodification. And we came up with a set of range of variables of those variables and trying now to actually produce polymer concretes within these variables and allow it to be 3D printable to make these structures of interest. We developed a model that shows actually that if we manage to do this polymer concrete, we actually will achieve a change in the vibrations significantly to actually completely die the signal. So the signal, vibrational wave signal, with the change of these polymer concrete properties will completely die within using 20 different polymer concretes 3D printed. Again, you don't have to do it to that level. You can just do, for example, 5 or 10, but it would result in elastic wave decay. So at the moment, what we are doing is actually doing that exact process I showed you to do the design of on the building of these acoustic wave polymer concrete structures using 3D printed polymer concrete. We have filed a patent for that this year, early in April, and we are in the process of filing final patent. So in conclusion, polymer concrete can lead the way to emerging technology. I've been working on this for a number of years, and I still believe it's a great candidate that has with a potential not used yet. We're talking about our interest in research is the 3D printable polymer concrete by design being developed at the University of New Mexico. And by considering the different factors I discussed, the mixed design, preliminary assessment, rheological and early edge assessment, computational simulation, performance characterization, and full-scale 3D printing, Design could be fine-tuned by utilizing different varieties of polymers, aggregate, fillers, and also by nanomodifications. The rheology of the 3D printed polymer concrete is very critical, is strongly governed by the polymerization rate of the polymer. So we will need to have work on the polymerization process and understand the polymer kinetics to be able to use 3D printed polymer concrete. Time-dependent failure envelope is important to build. We have a methodology to build it. We are improving this method. We published about it, but we are improving it as well. We are integrating the characterization and simulation to improve the quality and the success of our printing. To get a printed polymer concrete with a desired performance characteristics. At the end, we have also been patenting a new acoustic black hole structure using 3D printed polymer concrete, and we are developing a prototype at our lab now. Our timetable is to actually have a prototype by the summer of 25. Um, just some publications we've published in the past couple of years in these issues on the rheological evaluation and early age of polymer concrete. And we've been considerably working on this topic for a long time with the different nanomodified polymers to both using it in composites and in polymer concrete. The acknowledge, of course, a lot of these funding agencies and the industrial partners funded a lot of this work over many, many years on the back. I like to acknowledge the research team. Fortunately, I don't have a recent picture of the research team not added here, but I really acknowledge the students working with me and the team working with me on this today, including Siam Shanti and Daniel Murcia and Pablo. And I would like to thank you for your attention.
Thank you, Mahmoud. Thank you,
Hello,
Mahmoud.
Dr. Reda. Thank you so much
You're welcome.
thank you so much for your presentation. Yeah, it was a very nice overview of the polymer concrete. So our first question is, how do you compare normal concrete, conventional concrete 3D printing with polymer concrete 3D printing? And what are the challenges?
Both have, first of all, polymer concrete is a little different than normal concrete, okay? But both have the same challenges in 3D printing because they are not the typical material we used to use for the past 50 years, yeah? So there is difference in the using the normal concrete and 3D printing it. Same with polymer concrete. We do actually 3D printing of both. The challenges are similar. How can you make a mix today that is rather than the classical mix you used to have a slump and the compressive strength measurement, you actually need to account for a lot of the variables you have to do the 3D printing successfully and to achieve the mechanical characteristics required later and durability. So I think materials are very similar in the challenges. Materials are different because in the case of normal concrete, you have the cement and its hydration and a lot of its hydration kinetics issues and how to control it. Here you have a polymer and you have how to actually control it. So there is some difference in the base material, but the overall, they are very similar.
Great, thank you. So our next question is, what is the difference between the polymer concrete and polymer modified concrete, and what proportions have you already tested?
Great. As I showed in the very early slide, the person is asking, say, polymer modified concrete, that is also known in the literature as latex modified concrete. You can use both names interchangeably. In this case, you use amount of polymers. Usually a polymer latex, doesn't have to be, but it's usually a polymer latex. A latex is basically a polymer that has about 40 to 50% of its weight by water, is water. But basically you are adding this to your normal cement concrete. That is what's known as polymer modified concrete and latex modified concrete. Well known, used in the industry for a number of years. I've used it in projects myself. This is one type. The other type I'm talking here about is polymer concrete. There is no cement. This is a material that is used to make concrete without cement with a binder. Main differences are one, cost and applications. So, for example, latex modified or polymer modified concrete used a lot in bridge decks. because it's a one step further in durability to normal concrete. It has a lower permeability, a higher durability, but it is not as robust in durability to polymer concrete. For example, if you are making manholes or sewer tanks or chemical tanks, no polymer modified concrete will not survive it, but polymer concrete will survive it. So if you want to build a tank for chemicals for 100 years service life, polymer concrete will be the choice. So it's a different applications. The case, for example, we're describing here for acoustic black holes, normal concrete and polymer modified will not work. Application driven. The choice is application driven. Do you need this? Then the cost will be low. If you are making something, if you think of the life cycle cost, if you are making a structure that will survive aggressive environments for 70 or 100 years. We've done both. Cost, of course, is different, but life cycle cost is the key to show this material actually is lower cost.
Great. Thank you. Our next question is, what are the applications? You did talk about the application previously, but yeah, our question is, what applications do you are the potential for 3D, like for 3D printing this polymer concrete? Are there any structural applications? And if yes, what are those?
Of course, a lot of the work done in polymer concrete. So there are structural applications. There are elements used for example, machine foundations, heavy machine foundations, because the polymer concrete is well known for damping capabilities. Also, as I was explaining, if you have these tanks, for example, or containers to protect against aggressive environments, you are going to have these structural walls or structural elements. So it's not just a protection liner. It is a structural element that is reinforced with steel. And again, the ACI have ACI 548.6R, which is the structural use. That's a document done by the committee I-548, polymers and adhesives in concrete. And that is explaining the structural use of polymer concrete. We actually can design polymer concrete very well with steel reinforcements to actually work as a structural element. Of course, there are design guidelines and precautions need to be used because it's a little different than the concrete, or a bit different than concrete, but polymer concrete has been used in structural applications. As I said, in many of those structures, it will be used. For 3D printing, my take is a lot of the polymer concrete industry today is precast. 3D printing is a wonderful venue for precast. So rather than running a precast for a normal 8-hour shift, you could run the precast plant for a full day shift, 24-hour non-stop, because you are doing this to the robots. So I see that is a very, amenable for precast production. We've seen a lot of applications. For example, electrical boxes used in small and big sizes. Conduits, these are having earth pressures on them and very high aggressive environment in many cases. They are now produced by precast polymer concrete. We're offering a method to actually make this in 3D printing. Much more higher quality control in the material and much more precise production. So there's a lot of applications. And again, what we're talking here about acoustic black holes, this is a new application and a new interest. It has a lot of applications for the security and for the safety. So I see a lot of applications.
Mm-hmm. Thank you. Our next question is, are there any applications for polymer concrete in subground applications?
Of course. Good question. Absolutely. It is for subground. It is any application that has special characteristics, including aggressive environments. So in many times with subground, you have aggressive environments. There are two choices you can do. You can use a thin layer of a polymer protection with limited capability on the typical structural concrete, or you can use a polymer concrete. In the old days, of course, there was not a lot. Actually, the polymer concrete started in 1950 with great applications of the scientists and engineers that developed it from then to now. But there was always the risk. Yeah. Now, as we know more about the material, we are able to characterize more. And there is, as I'm repeating, there is ACI documents on how to design this material. I think it's going to be very soon using these materials in structural application, and it has been used for ground applications before, for large size conduits to actually protect cables and protect wire lines and things like this. It has been done before by the industry, and by the way, for also windmills. If you see some of the documents of ACI 548.6, I think it shows multiple applications that's happening for polymer concrete structural.
Mhm. Great. Thank you. So, our next question is, if I am a contractor and I would like to replace conventional concrete with polymer concrete, what applications I should think about and which will be more beneficial and cost effective for my projects?
If you have aggressive environments, the concrete is exposed into a high aggressive environments, then the polymer concrete would be a viable option. That will of course need to be assessed, by looking at the design, looking at the case you have for construction. But if there is aggressive environment, polymer concrete is an excellent option, and it's been used before on that. And
Great.
many other applications, I would say also the damping. If there are damping requirements on the structure, like we use, as I said, for windmills, we use it for other things, machine foundations, many of those that has damping requirements, polymer concrete provides excellent damping compared to concrete.
Okay, great. Thank you. Our next question is, you mentioned about ACI guidelines for polymer concrete. Are there any ASTM specifications
Of
for
course, there are ASTM specifications on polymer concrete as well. I think many of them is in polymer. There is polymer modified concrete ASTM specifications as well. Yes, there is. I don't know the numbers off the top of my head, but if you see the ACI documents, I've very visited, and I've been the chair of ACI 548 for 6 years, and I've been in this committee for the past 20 years or more. So ACI, you will find these ASTM specs that is relevant in these ACI documents as well. But there
Mhm.
are ASTM specifications.
Great, thank you. Our next question is, what? So what kind of polymers do they use in polymer concrete or polymer modified concrete? Are those same, or are what are the proportions used?
Okay, first, they are not the same, because as I said, the polymer modified concrete is a type of polymer you are going to mix with cement. So typically it is a polymer latex. So materials used in polymer latexes, including styrene butadiene rubber, acrylic, styrene acrylic copolymers, sometimes some special types of epoxies, but they are not the same used. This is the most common. SPR is the most common, styrene butadiene rubber. And typically it's used in about somewhere between 10 to 15% of the weight of cement. Again, we have ACI 548.3, and that is a document, and that is describing very well everything about polymer modified concrete, all the details, the types of polymer, the mixed designs, all of this, you will find it there. Now, for the typical polymer concrete I spoke about, that is where it replaced the binder, very different. You're talking about replacing the complete binder with a polymer. So the ratio here is the ratio of the polymer to the by weight, yeah, to the whole concrete. So you typically is in the range of about 15%. Lower than that, maybe a low 12%, 15 to 18%. Depends on the concrete strength and the expectations of the concrete. That is one. The different types, very different types. Polyester is very well known, vinyl ester. There is some increased interest in reducing the esters and their use in the industry. So that gets other materials like epoxies, like many other methyl methacrylate is very well known, very widely used in making polymer concrete. So different types of thermosets. We've been describing, and again, this is not in the industry, I'm just talking about it for future in the next 20 years. I think the high temperature thermoplastics will be used for 3D printed polymer concrete. Very amenable. They are used already for 3D printed composites. So I believe we are working to get them into 3D printed polymer concrete. But as I explained, vinyl esters, epoxies, and methyl methacrylates and other copolymers of them are in the market to be used for polymer concrete.
Great. Thank you. Our next question is, are there any suppliers for polymer concrete? Yeah, are there any suppliers for polymer concrete in the?
There are, but I don't want to be a sales guy. So there are in the US and in Canada, there are, and worldwide, there are suppliers. In the US, there is a number of them, many of them in ACI. I've worked with many of them. Many of them contributed to the ACI 548 work. I do not want to mention one and not to mention the others. So I am avoiding giving
Hey,
names,
Mahmoud,
but there are many.
Mhm. Great, thank you. So our next question is, are there any applications of polymer concrete? Uh, those those are fire resistant, or how would you deal with fire when it's polymer concrete structures?
There are paints that are used to achieve the same fire rating. So if
Mhm,
first of all, it depends. Again, polymer concrete, I wouldn't use it. Again, we talk about applications. Yeah, I wouldn't use polymer concrete to make the core of a building or a structural column. That's not the objective. But if we are using it for a structural reasons, for example, like I said in tanks or in other applications where it's used structurally and it has a structural performance and you want to fire protect it, then there are paints actually used in the industry to achieve a fire rating acceptable to that application. So there are ways to achieve a high fire rating.
oh, great. That's great to know. Like
And there
fire.
is research funded. I
Mhm.
don't know. I don't know how is it next or ACI Foundation, but there
Yeah.
is research funded at the moment about the polymer concrete fire rating.
y-
And again, Nix can provide information about this and the fire capabilities and properties of polymer concrete. And have been in communication with the research team. So we're expecting their work, but it is outside the research should as the research will answer the question, provide alternatives. But I'm telling you, in the
mhm,
industry, it has been used, paints already, in case of, for example, in tunnels, that is
mhm.
using polymer concrete structural elements, it has been used to provide the necessary fire rating for this material.
Great, great. Just to add what Dr. Taha said, yeah, Next has funded this research to increase the fire resistance of polymer concrete, and it is funded to Dr. Kodur from Michigan State University.
That is
He's
correct.
working on it. Mhm.
Yeah, and
Thank
they
you.
have great potential, great lab, and did a lot of work on fire resistance in concrete before. And I'm very pleased that they are looking at this because you need special facility to be able to do this. And you're doing a great job. So I'm looking forward to have this published in ACI and included in the 548 documents.
Mhm. Great, thank you. We have last two more questions. I'll just quickly go through it. Our next question is, what do you think about so the 3D printing concrete is already a new venture in itself, and when you talk about polymer concrete and in 3D printing, how do you see it comparable to current 3D printing market? Are there any potentials, or is there any reason why you want to go to polymer concrete 3D printing side?
Good. First, the reason I'm going to polymer concrete 3D printing because I'm a polymer concrete guy. So I do concrete as well, but that's my specialty. So, but let me explain. First, the polymer concrete is not a new material. From the same range of new, it's been developed, used in applications since 1950. So we have, and that typical material I'm talking about, not just the latex modified, the polymer concrete, polymer modified concrete. This is since now we're talking about 80 years was used. Significant use in Japan, in South Korea, in many countries used polymer concrete extensively, and in the US and Canada. Okay, so that's one. So there is, it's not a new. Now, why 3D printing? Because as I explained, a lot of the work in polymer concrete is happening in precast. A lot of it is precast. And 3D printing is actually making that precast of a higher quality and would make it from higher quality and higher precision. So it's the next logical step is to make 3D printed polymer concrete. That's one. Second, there are applications that would require 3D printing. Normal concrete is not going to work for it. One of the biggest applications, one of the biggest, not application, but I would say advantages of polymer concrete is a very high bond. So you do not have the bond of normal concrete. You have order of magnitude bond. So polymer concrete has a lot of advantages that will bring it to the table, and it need to be 3D printable. I think there is the road from here for polymer concrete actually is going to be much bigger. I already spoke to a number of companies of interest to do this in rail. So we are just behind in doing enough research to support them, but there is big interest.
Great, great. Thank you so much. Our last question is, we are going forward with sustainability and lower carbon footprint. What do you think, how this polymer concrete will lead to us? Please give some insight on carbon footprint and sustainability of polymer concrete, and where do you see the future?
Wonderful. I really like the questions. I need to say I have great set of questions for me to write in the future and things. Okay. Of course, it's an issue, yes, for all the cement and polymer concrete in the future, sustainability and the carbon footprint. Two things here to think about. My 2 cents on this. One is anytime we think about carbon footprint of materials, I strongly think, and we've shown this in publications and we've seen it by others, we got to think on life cycle. If you are going to make a bridge deck that's going to last 20 years, yes, then and you replace it every 20 years, then for 100 years, we should calculate your carbon footprint for the 100 years. Yes. If I'm making a polymer concrete with a base material that is typically as polymers, many of it is hydrocarbons, that has a higher carbon footprint, but in 100 years, you do not need to replace it, then that's the comparison. The comparison shouldn't be done with the carbon footprint of today. Let's just calculate materials carbon. That's not the way. We actually showed, we have a publication showing how to calculate this for polymer concrete and based on the different materials involved. But there is another point also that is coming through, and we published about this last year on some use of biopolymer concretes. So there are coming in the market biopolymers where actually they have a negative carbon footprint. So they are from sustainable resources, and they are in the market today. So we actually produced polymer concrete. I believe, just from the top of my head, I think 3,000 to 5,000 psi concrete with polymer concrete with the biopolymer. So it's a very viable material that can be used in producing 5,000 psi concrete and higher. But that was our target, was just making. So that research is important, and looking on sustainable resources for the polymers, which I think is going to happen. But in the meantime, we got to think of life cycle. We should not think of it as a scalable number, just one number to compare.
Yeah, I think it's very important to do the study from I think it says cradle to grave, right? Yeah.
That's correct.
Mhm.
Absolutely, Amar. Absolutely.
Yeah, great. Thank you so much for answering all the questions. It was nice talking to you on all these questions, and I hope and I believe it's not hope, like the audience really loved your presentation. Thank you so much, Dr. Adataha, for this.
Thank you very much. Thanks for the opportunity and for ACI and for Next. And we'll for this window of opportunities and for supporting our work, which we really appreciate. And we'll continue looking at these materials and hopefully provide more answers. Thank you.
Great. Sure. Thank you.